Okay, conservation of momentum. So momentum, you guys know the character for that is lowercase t. It's a vector. Sometimes I put those vector arrows above the variable. I like to do that for momentum especially. That's mass times velocity. So how massive is something and how fast is it moving? You multiply those together. Okay. And vector quantity means that the direction matters too. So if they move to the right, someone's moving to the left. You have to consider that. You can apply conservation of momentum to collisions. Anytime you see a collision, think this framework or something to do with momentum or momentum conservation. Say conservation of momentum for a closed system. Looks some version of this: sum of momentum before the collision equals sum of momentum after the collision. Okay. Now, closed system, that means there's no external force, right? Okay. Now, that might change later when we do force versus time graphs and get impulse. That does imply an external force acting on some object or some system. But if there's a closed system, got objects colliding with each other within that closed system, then you can say something. So all the momentum bits added up have to equate before and after. Okay. So for example, what if you have a couple of asteroids and say mass A moving at some velocity A initial, and then I've got some other asteroid over here, some mass B, and maybe it's a head-on collision this way, velocity B initial, something like that. Okay. And then two, bam, collide. Okay. And then, well, they might do a number of things. It depends on the materials they're made of. They might collide and stick. They might boing, bounce off each other. They might bounce off each other in a number of different ways. We just draw a generic case of them bouncing off each other. So mass A, and then velocity A final. And then over here, got our mass B and velocity B final. Okay. That could be the case, right? Okay. Now, how does this scenario that I just drew appears before the collision and after the collision? How does that align with this conservation momentum framework? Can you guys write out an equation for this picture based on this framework? Can you guys do that? Just some generic collision. Trying to give you guys a head start. Because if you guys can beat me to the answer, then that's a really good indication that you're ready for this exam. Did you guys write that? Mass times velocity of each bit before the collision equals mass times velocity of each bit after the collision. Okay. Also, remember that these are all vector, well, the velocities and momentums are vector values. So the fact that I have opposite directions for the motion, right? One's moving to the right, one's moving to the left. Okay. I do need negative numbers somewhere, right? Someone's moving to the right means positive, left it could be negative, for example. Okay. All right, then. Oh, yeah.
How do you find the speed of the center of mass?
All right. Center of mass. Right. How about this? What if these two asteroids? I'm going to start with the simple one and make it more complex. What if they were the same mass and they started off at the same speed, just opposite direction? What would the center mass speed be? Same mass, same speed, opposite direction. Would it just be like hanging out there, like not moving? Right. Then if they collide, bam, maybe they collide and stick, maybe they bounce off each other. Before and after the collision, does the center mass change what it's doing? No, it just stays doing what it was doing. So in that example, what about this though? What if mass A is larger than mass B? And maybe they have comparable speeds so that mass A has more momentum than mass B. Maybe this is like 100 units of momentum. Maybe this is like negative 50 units of momentum. Like 100 plus negative 50, 100 plus negative 50, right? Okay. So you have something like this, like bam. Right, or like bam, right? So do you think the center of mass would be overall moving to the right? Yeah. And then actually you could figure that out by doing 100 plus negative 50, and then taking that and dividing by the sum of the masses. That would give you the speed of the center of mass, and it would be, say, to the right. Okay. Now, after that collision, would the center of mass still be moving to the right? Yes, it would. In fact, if you only focus on the center mass, you would never even know when the collision happened, right? Isn't that true? Right. Actually, there's a really good chance that you're going to get one or maybe two questions on exactly what I just told you. So that's worth 1, 2 AP points right there. Okay? Is that the fact that for a closed system, before and after a collision, if you just focus on the center mass, you would never know when that collision happened because it just keeps on doing whatever it was doing. Okay? I think I might ask you guys like a throwing a snowball question. You know what? I got to set up. It's that principle, but I got to set up a inelastic and elastic collision. Right? You guys ready for inelastic collisions? Okay, ready to move on? And so, inelastic collision. Right. This is one extreme form of collision. Remember, if two objects collide, are we talking about? Are we talking about super bouncy, or are we talking about collide stick, or are we talking about like two half-played tennis balls that bounce off each other but not very well? This could all be consistent with this conservation of momentum. Right? But now let's look at, say, like boundary conditions, extreme type collisions. And this is one of AP is much more likely to ask about this type of collision because the math is a lot more straightforward. Can you guys write out a conservation of momentum for this type of collision? Can you guys do that before I do? But you guys beat me to the answer. Is that what you guys just wrote? Right? Because inelastic means they collide and stick, right? So if they collide and stick, maybe they're individually, might even start off with like two individual asteroids, and they like bam, they stick together, right? Well, if they bam stick together, when they make one giant mass, maybe get some common final velocity, right? Okay, so that represents inelastic collision. And if AP wants you to like sit down and solve like for some numbers, like what is the post collision final velocity? They almost always ask this type of collision. Okay. Now you can also do this sort of in reverse, and that'd be the example of like throwing a snowball, throwing a baseball, and they usually have some version of like you're on a frictional surface, or you're standing on ice, right? And maybe you have a closed system that includes like the person plus the snowball, or the person plus the baseball standing on like frictionless ice. Right? How can you modify this equation to represent throwing a snowball on a frictional surface? Can you guys do that? Did you guys write that? Right? Okay. Yeah. So it looks like the person on the snowball is starting possibly stationary. Maybe be not, could possibly be zero, right? Just like send it, right? And then the person throws the snowball. So it looks like the mass of snowball heads off one way at one speed, and the person heads off different speed the other way. Right? And if this did start off at zero, like you start at rest, just standing, say on a frozen lake, right? Then when the snowball and the person have to have opposite momentum values from each other, so maybe like a positive and a negative value, right? I mean, remember, these are vector values, so look for negative values, right? How about this? Let's say that you ran kinetic energy checks on all these situations. I mean, yesterday, last week, this whole last week, we've been looking at energy conservations, right? But then I've been saying for collisions, you specifically want to switch over and do momentum conservation. But then what if you ran a check? So let's go back to these asteroids, just some generic like collision and bounce off each other, right? And they might bounce off each other one of a million different ways, depending on how bouncy they are, coefficient of restitution. Okay? What if you looked at the kinetic energy before the collision and the kinetic energy after the collision? Would the kinetic energy equate? Actually, it would, but for one specific type of collision, only for one type of collision. What's the only type of collision that the kinetic energy is the same before and after? Elastic. Has to be perfectly elastic, which is pretty closely modeled by Newton's cradle, right? Because we're talking about perfectly bouncy. That's probably as close as you're going to get, right? But in general, is kinetic energy conserved? No. Is there, say for like these asteroids, what if they're like, bam, so they bounce off each other, but not very well. Is there more kinetic energy before or after the collision? Before. Yeah, before. What about this? What about what if they collide and suck, like, or like collide and stick together? Is there more kinetic energy then, before or after? Still before, right? What about this? What about the guy throwing the snowball? Guy throwing the snowball. Is there more kinetic energy before or after? Oh yeah, after, right? Yeah, after. Now, why would that be the case? Well, this is kind of backwards to this, right? If he starts at rest, doesn't he have zero momentum and also zero kinetic energy? But he throws a snowball. Now there's lots of energy. Wait, does that break conservation of energy? Where did all that energy come from? Came from his muscles. Isn't it true? If you throw something, maybe it's stored chemical energy. That's where that energy came from, right? And then what if you filmed this guy throwing the snowball? So he's standing at rest with the snowball, then he throws it, snowball goes one way, he goes back the other way, like rebound. Right? Do you guys remember Magic School Bus Split on the frictionless baseball field? Same type story, right? What if you ran that film in reverse? Wouldn't it look like the snowball and the person go and come back together? In that case, you say, well, there was more kinetic energy when they were in motion compared to when they were not moving, right? Something like that. Right. Let's look at I know I mentioned elastic, but let's switch over and look at elastic collision. Right. Elastic collision, looking for two conditions in terms of physics equations. Yeah, sure, you want momentum to be conserved, but that's true all the time anyway for any type of collision. But also, what else is conserved again? Kinetic energy. So kinetic energy before equals kinetic energy after. Notice I did not put arrow vectors on kinetic energy because kinetic energy is a scalar, right? And energy is a scalar value. Right? So you'd have both these conditions specifically for this type of collision. Now there's a solution to that system equation. Actually, let me draw it. I know I've got a poster over there. I can barely read that poster. So let's see, velocity of object A post collision is equal to, it's a big old ratio. What's that say up there? Velocity A before times the difference of the masses plus, I think it goes 2 mb vb naught, all divided by the sum of the masses. I think that's it, right? Is that right? Right? No, that's a pretty crazy solution, right? You don't have to memorize that. AP almost never asks elastic collision questions, right? I can think of two that they've asked before, and I'll tell you what those two questions were, where I've seen them talk about elastic collisions. One question I've seen AP ask about elastic collision is some version of, there was one mass just at rest, just sitting there, minus some business, and there's another mass, identical mass that runs into it. Whoops. So much for that. And the question was what? Well, after the collision, what happens to the speed of the other one? Doesn't it exactly transfer its speed? Right? Because it transfers the momentum. And if it's perfectly elastic, then, well, kinetic energy is also transferred. So it's just like a perfect send off. It's like, bam, bam. Right? You guys see the switch? It's just like, bam. And then this one takes off and this one's at rest. And it's slow mo, bam, bam, bam. Right? That would be for elastic. Right? So that was like a middle step in some longer FRQ. The other question I've seen them ask for elastic collision was, they said they gave you multiple choice possibilities that something is elastic, and they showed two objects colliding and said after the collision which would be possible, and they gave different speeds, and you had to by yourself go through and check this condition. You had to get 1/2 mb squared plus 1/2 mb squared equals 1/2 mb squared plus 1/2 mb squared. So I think the best way to handle something like that would be go through the choices, option A, option B, option C, option D, until you satisfy this condition. Right? Actually, let me write out this bottom condition. I should do that. Because I'm telling you that the answer to this system is this crazy system. But you don't really have to know this for AP. Right? What does that actually look like? Can you guys beat me to the answer too? Sum of kinetic energy initial equals sum of kinetic energy final. Okay. When I say this, can you guys write that out long form for, like, very simply two objects colliding? Okay. Yeah. Is that what you guys were thinking? Right, all the 1/2 mv squared bits have to equate before and after, right? Right. Now, how can you quantify how bouncy something is? I mean, we've got the two extremes here. Inelastic collide and stick. AP is probably going to ask some questions about that. Elastic, they collide and bounce off each other perfectly. Kinetic energy is conserved. You probably won't get a question about this. If you do, there might be one, and they'll probably keep it pretty basic where you can navigate this. But what if it's something in between? Isn't it some coefficient of restitution? You guys remember that? Now, AP is not going to ask about that, but just verbally real fast. Coefficient of restitution is if two objects bounce off each other, what's the difference in velocities after the collision compared to before the collision? And it's always going to be something between 0 and 1. Okay? So 0 would correspond to inelastic, 1 would correspond to perfectly elastic, but AP is not going to ask that. Something else that they're not going to ask, which would probably be a good thing maybe for college, might be like a glancing collision in 2 dimensions. So what if you have like what's one of the strike balls in pool? Is the 12 ball strike? It's about 12 ball. Okay. So you take the cue ball and let's say you hit it, so like, bam, it like hits on an angle. Okay. And the cue ball takes off this way and the 12 ball takes off this way. Okay. Could you, that would be a collision. It'd probably be pretty close to elastic. You might be able to use that as a model. Okay. How would you figure out like what speed and which direction these things move? Okay. And I can tell you real fast, just the basic setup for those. What you would do is you'd say that momentum is conserved along each axis. So here I'm looking at post-collision. Okay. I would say that the momentum up for the cue ball equals the momentum down for the 12 ball, this is along this y-axis. Okay. And also the forward momentum has to add up to the original momentum of the cue ball. So this mass times velocity has to be these pieces added together after the collision. Okay. AP is not going to ask that though. Okay. You know what they will ask? You know what you will see for sure? You guys might see something that I know you're going to see on the exam. Force versus what? What am I going to write right here? Time. Force versus time. Okay. Now this graph might look. It might be a number of different things. It might be a nice clean graph. It might be a scatter plot. It might be rectangle shape. But probably. Actually, it's probably not going to be a scatter plot. Could be. Okay. It's really common for these graphs. They don't have to take the shape, but they oftentimes do. Take like a triangle type shape. Okay. And an example of this might be, say, a bat hitting a ball, okay, where you might have an open system that consists of only the baseball. Maybe this baseball could be an open system, right? And there's a net force acting on that ball, which causes it to boing, it changes momentum, changes speed, changes velocity, definitely change direction. And what property of this graph would you care about in solving a question like that? Area under the curve. Because this area under the curve represents what physical property? Impulse. Exactly. That's change in momentum. Change in momentum. Can you guys write out the impulse formula before I do? Impulse. Change in momentum. Can you guys write out the formula before I do? So change in momentum. That could be mass times change in velocity. Okay. Although you could have changing mass if you have something like a conveyor belt and maybe there's some mass being dropped on it. You can apply this a little bit differently. But let's just stick to this because this is probably what you're gonna get. Okay. And where does that come from? Mass times change velocity is equal to what times what? Force times time interval. Okay. Right, another chair. Now, the way I wrote this, it does imply a constant force, and my graph is a variable force. Okay, so maybe these don't exactly align, sort of, or unless I call this a what kind of force? Average force. Right. And where is average force on this graph? Let's say the peak force here is like 100 newtons. Let's say F max is 100 newtons. Right? Is that 100 newtons? No, this is how many newtons? 50, right? I mean, if it's a triangle shape, right? Probably be, actually it would be half that, right? Triangle shape would be half that. Because look at this. If you do delta t, isn't that like from here to here? Isn't this your delta t, your time interval, right? The base of that triangle. Okay. And if you multiply it by 50 newtons, which is halfway to the top of that triangle, wouldn't they give you the area of this here rectangle? Is the area of this rectangle and the area of that triangle the same area?
Yeah.
It is, represents the same impulse. Okay. So then you might do something like this. Momentum final equals momentum initial plus the change in momentum, which of course would be the area of that graph. Impulse. Okay. You guys can do that? Yeah, you guys are gonna get questions about that on the exam. I mean, you have to. There's no way they couldn't ask questions about this. Same thing with work as force times distance. If you saw force versus distance, then you know the area under that graph would represent the work done, like a change in energy. Okay, you're gonna get questions about this. All right, you guys good so far? All right.